Hello friends, welcome to our channel. So today in this video we are going to discuss about the entropy change in an ideal gas. So first, the definition of entropy is ds is equals to dq for a reversible process divided by t. So take this as equation number 1. In this equation, S is entropy of the system, Q is heat transferred, and T is temperature. So while moving T to the left hand side, we get T ds is equals to dq reverse. So we know TdS is equals to du plus pdv. Substituting the value of TdS in the above equation, we get dq is equals to du plus pdv. Take this as equation number 2. So in this equation, U is internal energy of the system, P is pressure, and V is volume, Q is heat transferred. Now dividing equation 2 by T using the definition of ds. So we get, that means we are dividing this equation by T. So we get ds is equals to 1 by T into du plus P by T into dv. Take this as equation number 3. But we know that du is equals to Cv into dt. So substituting the value of du in equation 3, we get ds is equals to Cv by T into dt plus P by T into dv. Take this as equation number 4. We know that for ideal gases, PV is equals to nRT, and while we taking the value of P is equals to, we will move to right hand side, so it will become division, nRT divided by V. So substituting the value of P in fourth equation, we get ds is equals to Cv by T into dt plus nRT by Tv into dv. So that is equals to, this T and T will get cancelled. So ds is equals to Cv by T into dt plus nR by V into dv. Take this as equation number 5. So now, to get the definite change in state, we are integrating equation 5. So this is equation 5, that is ds is equals to Cv by T into dt plus nR divided by V into dv. So while integrating this fifth equation, we get del S is equals to integration T1 T2 Cv by T T into dt plus nr is constant, so we are taking it out. Nr integration v1 v2 dv by v. Take this as equation number 6. If Cv is constant, while further differentiating this equation, we get del S is equals to Cv into ln T2 divided by T1 plus nr ln V2 divided by V1. Take this as equation number 7. From this equation, we know that yes, that is entropy is always positive. Second is entropy of an ideal gas increase with increase in volume. The equation 7 is the equation for entropy change in an ideal gas at constant pressure with change in volume. So next we are going to see the equation for entropy change in an ideal gas at constant volume and change in pressure. So now the entropy change in an ideal gas is expressed as T ds is equals to dH minus VdP, where T is temperature, S is entropy of the system, H is enthalpy, V is volume and P is pressure. Now taking the value of ds, that means we are moving T to right hand side from left hand side. So ds is equals to 1 by T into dH minus V by T into dP. But at the same time, we know that the enthalpy of a system, that is dH is equals to Cp into dt. So while substituting the value of dH in the above equation, we get ds is equals to Cp by T into dt minus V by T into dP. So take this as equation number 8. We know that for an ideal gas, PV is equals to nRT. So while taking the value of V, P will move to right hand side, so it will become division. So V is equals to nRT by P. So substituting this in the above equation, we get ds is equals to Cp by T into dt minus, we are substituting the value of V in here, so nRT minus divided by P into T into dP. So while T and T get cancelled, ds is equals to Cp by T into dt minus nr upon P into dP. Take this as equation number 9. So while integrating the 9th equation, we get we get del S is equals to integration T1 T2 Cp by T into dt minus nr or constants, so we are taking it out, nr integration P1 P2 dP by P. Take this as equation number 10. So while further integrating this, if Cp is constant, we are taking it out. So further integrating equation 10, we get del S is equals to Cp ln T2 upon T1 minus nr ln P2 upon P1. So take this as equation number 11, and this is the final equation. From this equation, we know that the entropy of an ideal gas will decrease with increase in pressure at constant volume. So that's all for this video. Thank you, friends.